Okay, so we start to look at Newton's laws of motion. Don't forget the first law of this idea of inertia is that the object's velocity will stay the same unless an unbalanced force acts. So if the forces are balanced, it will just keep the same velocity, the same speed, the same direction. But if the force is unbalanced, it won't actually apply. So you can think of something resting on the table where there's a weight force acting on the dish, but there's an equal and opposite force acting up. So those forces are balanced because they're equal and opposite. So the object will maintain the same velocity. And things with more mass also have more inertia, and they'll tend to do that even better and keep that same velocity. Okay? Some other examples we looked at is if you're in a car going at 60 kilometres an hour and you don't have your seatbelt on, if the car suddenly stops because it has a brick wall exerting an unbalanced force on it, the person will keep on going at that 60 kilometres an hour until they encounter some sort of force. So it keeps that same velocity until the force acts. If the bus is at rest and you're standing up in a bus and it suddenly takes off, your whole body is at rest or will tend to stay at rest. The exception is your feet. Because of friction between the feet and the floor, it will actually get dragged forward and you'll feel like you're being pulled backwards, but what's happening is your feet are just being dragged forwards. Same if you're going around a corner, velocity includes size and direction, so it will try and keep the same direction and slide off to the side here. And certainly if you remove that force here due to friction, by putting oil on the tyres or on the road, it'll just slide off and continue. So you do need a force to cause it to change. So it wants to keep the same speed and the same direction and whatever that is, even if it's at rest, to actually maintain that idea of inertia. But something with more mass has more inertia, just bear that in mind. And don't forget, mass is fundamental. It's how many kilograms or how much matter is in an object, whereas the weight is how much force is on it due to gravity, and you can work that out by using a formula called F equals ma, which brings us to the second law. So in the second law, if an unbalanced force does act, then this time the velocity does change. It will actually accelerate in the direction of that force. And it turns out the size of the acceleration is proportional to the force. And what that means is if you get double the amount of force acting on an object, it will accelerate at double the rate. Okay, so it speeds up twice as fast. So that's directly proportional. If you do 10 times the force, you'll get 10 times acceleration. However, if you get something that's more massive, it's actually harder to accelerate because it's got more inertia. So that's actually called inversely proportional when it's over that, A proportional to 1 over M. And in that case, when you get 10 times the mass, the acceleration is going to go down by 10 times, or in this case here, if the mass is doubled, the acceleration is halved. But if you put the two ideas together, you get this formula A equals F over M, or F equals MA is how it's often used. Okay? So if you do get a question involving the numbers here, the first thing you need to do is work out the total force. So if we look at this one here, what we've got is got a car with an engine force forward. Basically, by pushing the wheels back on the road will push it forward by 4,000 newtons. But the end result is a 4,000 newton force due to the engine pushing through the wheels. If you said the total friction and drag force back on the car was 1,000 newtons when it's driving along, the net force or the overall force or the unbalanced force or the total force or the sum of the forces is going to be 4,000 forward and 1,000 backwards. You're going to get 3,000 newtons to the right. Okay? So it's the overall unbalanced force that accelerates the car. So that's what you would put into the formula F equals ma rearranged to that direction there. So 3,000 newtons divided by a mass of 1,500 kilograms tells you that the car is going to be going with an acceleration of 2 meters per second. So it accelerates 2 meters a second faster every second in the direction of the force. Now the third law is for every action force you get an equal and opposite reactions force. Now it's actually better to say that when one object exerts a force on another object, this second object will exert an equal force in the opposite direction back on the first one. So they're in equal pairs in opposite directions at equal size. Okay? So for example, if the hammer pushes a nail down with a force of 10 newtons, there's a force of 10 newtons of the hammer on the nail. But and that will actually push the nail in, that's the actual action there. And the reaction to that is that the actual nail will push forward back on the hammer with a force of 10 newtons up. And that will slow the hammer down and decelerate to a stop in the opposite direction. So force is always in pairs, so you could have swimmer pushing water backwards and the swimmer gets pushed forwards. With a rocket, the gas particles come out the back at high speed, so the rocket gets pushed forward by the gas with an equal force and an opposite one. So what about if a bug hits a car, or a car hits a bug rather? If you've got a fly hitting a car and the car's going 100 kilometres an hour, is the force on the fly the same as the force on the car? Well, according to Newton's third law, it is. The force is supposed to be in equal pairs and opposite. However, because the actual fly is so much more smaller in terms of mass, it will get a much larger acceleration for the same force. And the very massive car will hardly experience any acceleration for the smaller force, okay? Sorry, for the same force. And that applies to anything. So whether it's a gun and a bullet, so if a gun fires a bullet out, the force pair here is still equal, okay? But because A is equal to F over M, for the same size force, a much bigger mass will have a much smaller acceleration. So the gun at recoil is a lot smaller for acceleration, whereas acceleration here is very big because the mass is very small. So you have to take both of those things into account for a cannon firing a cannonball, or a gun firing a bullet, or you hitting a bug rather than a large object like a kangaroo, in which case there would be a fair bit of deceleration on the car. Okay? So I can now illustrate that with a version that I did a couple of years ago, so you'll see a shot of me now being much younger. Okay, thanks. This. And you put them with the same mass to start with like that, and let them go. Okay? And just knock them off there. The spring-loaded one here, so cart A will push cart B forwards, but cart B is also pushed backwards by the second cart. So they have an equal force on each other, but they also have equal accelerations in this case because the masses are the same. If you go and load up another cart now, like this one here, and actually load this up with something, say 5 kilos then, so we actually increase this mass by a fair bit. It's probably close to 8 times now. When you do the spring load this time, and I'll just put that in the right position there, when you put the spring load this time, the recoil is a lot smaller on the more massive cart. Are the forces still the same? Yes, they are. But the effect is different because of the difference in mass. The second law says more mass, less acceleration, while the third law is saying equal forces, opposite directions. Okay? So just bear that in mind there.